You tap your phone's screen. The glass reacts instantly. No button moves, nothing clicks, yet your touch becomes a command. How does a perfectly flat sheet of glass know exactly where your fingers are? In this video, we will go under the glass and see how modern touchscreens actually work. From invisible electric fields to clever software that tracks every finger. To understand that, we need to look beneath the surface. A modern touchscreen is not just a piece of glass. It is a stack of ultra-thin, carefully engineered layers. At the very bottom, you have the display itself. That is the part that creates the picture with tiny pixels lighting up in different colors. Above the display, there is a transparent grid made of tiny, almost invisible electrodes. They are arranged in rows and columns, like a spreadsheet made of glass. On top of everything sits the cover glass you actually touch. It looks like a simple surface, but just below it, that transparent grid is constantly watching for changes in an electric field. Most phones and tablets today use something called capacitive sensing. The idea is based on electricity and tiny electric fields. The touchscreen controller sends a weak signal through the electrode grid. This creates an invisible electric field just above the glass. As long as nothing is touching it, the system knows its normal, untouched state. Your body is slightly conductive. It can store and move tiny amounts of electric charge. When your finger comes close to the glass, it disturbs that electric field. At the exact point where you touch, a small amount of charge flows. The local electrical capacitance changes. The electrodes right under your finger sense that change instantly. So to the controller, your finger is not just there or not there. It is a precise, measurable change in the electrical behavior of that tiny spot on the grid. The electrodes are arranged in rows and columns. Think of it as a transparent grid covering the whole screen. The touchscreen controller rapidly scans each row and each column, one after another. When it detects a change on one row and one column at the same time, it calculates that intersection as the exact touch point. This scanning happens thousands of times per second. To you, it feels instant. To the hardware, it is a fast loop of measurements and calculations running non-stop. The same idea explains multi-touch. Because the grid covers the entire surface, several rows and columns can change at once. The controller does not just find one intersection, it can track multiple touch points at the same time. Meanwhile, the software is building a live touch map, frame by frame. A light, quick tap becomes a button press. A longer contact becomes a long press. And a smooth movement across the map becomes a swipe, a scroll, or a pinch to zoom. Real life makes all of this much harder. Water on the screen, humidity in the air, or electrical noise from chargers and cables can all disturb the signals. If the screen reacted to every tiny fluctuation, it would trigger random touches constantly. So the controller applies filters and thresholds. Weak, unstable signals are ignored. Only clear, consistent patterns are treated as real touches. Then there is palm rejection. When you rest part of your hand on a tablet, it creates a large, blurry area of contact. The software is trained to recognize these broad, low-precision shapes and mark them as background, not as intentional input. A stylus, on the other hand, creates a sharp, focused signal. The system can track its tip very precisely, and in many devices, it can even measure pressure and tilt. That is what allows you to draw thin lines, thick strokes, and smooth curves with high accuracy on a glass surface that still feels completely flat. Not every touchscreen works this way. Older devices, like early GPS units or cash registers, often used resistive touchscreens. Those rely on two flexible layers that physically press together when you push on them. They work with any object, a finger, a glove, even a plastic pen, but they are less sensitive and not as smooth for the gestures we expect today. Modern capacitive screens are different. They sense changes in electric fields instead of mechanical pressure. That is what gives you fast response, fine control, and fluid multi-touch gestures. So the next time you swipe through photos or pinch to zoom on a map, remember what is happening under your fingertips. A layer of invisible electronics is constantly measuring tiny charges, filtering out noise, and tracking multiple contact points at once. To you, it feels like simple, direct touch. Under the glass, it is fast, precise, and carefully engineered physics. Knowify, smart ideas simply explained.